Hello again, everyone. Let's wait for a minute. All right, let's continue. So, therefore, the first uh, point of this convex hull problem is to show, okay, we have made some geometric observation, we have turned it into an algorithm, but the algorithm turns out to be inefficient. And also, when we discuss degenerate cases, that may cause some difficulties to our tests. And also, what about robustness? We can have because because of floating point operations, we may have edges that multiple. This R, for example, it can be sometimes considered outside, sometimes inside when the points are very close to each other, or when a point is very close to a line between P and Q. We can have situations in which the edge list may contain some additional edges at the end which cannot be part of the chain, or it may be the case that the chain we cannot form a closed chain of edges because of these floating point errors. So this can actually cause the algorithm to crash. If you're, for example, your goal is, you may, or it may output something that is not even a polygon. All right. For example, if you cannot have a chain of edges which are not or it may stuck in an infinite loop. For example, if you have in step 8, if you say that find look at all the edges, or it's not stuck in an infinite loop, but it will basically crash trying to find an edge in which the starting point is R, or it will not be able to fill in these edge chain if some of the edges gone missing because of these simple floating point operations. So another important thing of a geometric algorithm is its robustness. Sometimes we just use integers. There are some problems just use integers to get rid of these problems, but sometimes even in the case of these small floating point errors, we may want to give the user something that looks like a convex hull, an approximation of it. For example, what I'm saying is that the convex hull, which doesn't include R in it. I mean, if I have a polygon, which is Q, this one, this one, this one, and P, and back to Q, is also a convex polygon. Or you can say PRQ. You can include R in your polygon, but as long as what you're reporting is a valid convex polygon, it may still be an accepted approximate result. But in this case, it is not the approximate solution that is given. Actually, the algorithm just crashes. What it's giving here is not even a simple polygon. In here, it's not even a polygon at all. There are some unbounded regions. There is no edge. So even in the case of errors, floating point errors, the algorithm should be robust enough to output something that looks like the real result. It shouldn't just crash. Okay, so these are the things that make computational geometry problems difficult. And the book then says that, okay, this n-cube solution is not good at all, so let's try to develop an incremental algorithm. And the incremental algorithm will be, it's a very simple algorithm that is described here, which just processes these points in sorted order with respect to their x coordinates. And it assumes that there's a order of points. I mean, no two points have the same x coordinates, so that there is a unique ordering of these points. But if they have, say, the same x coordinate, we can actually solve this problem by saying if they have the same x coordinate, then look at their y coordinates. In other words, use a lexicographic ordering of these points, if just considering them as if they are words with two letters. Okay, if their first letters are the same, look at the second letters and based on that, order them. So if they have the same x coordinate, if these are distinct points, if no two points have the same coordinate, if they are distinct different points, even if 2 points have the same x coordinate, their y coordinates will be different, and you will be able to sort them based on that. So there can be a total order, a unique total order among the points with this simple modification. Okay, so the algorithm starts by this more efficient algorithm that I'm going to describe. It starts by sorting the points with respect to their x coordinates. So the point with the smallest x coordinate will be p1, and the point with the largest x coordinate will be pn. Okay, now and it will process these points from left to right in this order, and by going from left to right, it will first construct the upper hull of the convex hull. Then by using the same process, but this time going in reverse order from pn to p1, it will construct the lower hull, and then it will just merge these two hulls one after another, which will give us the convex hull. All right, now let me make a statement, and I want you to tell me whether this statement is true or not. Okay, my statement is, if these points are sorted with respect to x coordinate from p1 to pn, my claim is that p1 and pn have to be on the convex hull. Is this correct? You can write in the chat box your answer. Is p1 and pn have to be on the convex hull always? Again, the p1 is the point with the smallest x coordinate, pn is the point with the largest x coordinate. Yes, they have to be on the convex hull, because they are extreme points. There cannot be a convex polygon which doesn't include them as their vertices. All right, so they will be outside the hull. If they're not in part of the convex hull, it means that since that's the smallest point in the x direction, if you have a polygon that doesn't include that, that will not be a convex hull. All right, so they have to be. So p1 and pn have to be on the convex hull. So we already know that. So the algorithm is like this. It starts with p1 and p2. p2 can actually be this point. Let me just zoom in on this, and I'm going to copy this on GIMP and try to work on it. Let's start with this new one. Okay, so let's look at our points. Let's call this p2, p3. So the points will be sorted. This is p4, 5, 6, 7, 8, 9, 10, 11. It goes on like this. Okay, so initially p1 and p2 are on the upper hull, and what we will be maintaining is that we will be maintaining the current hull, which is correct up to point I. For example, when we come to point 10, upper hull will include p1, p3, p6, p9, and p10. It's going to include points such that all the points to the left of, for example, when I come to p10, okay, the upper hull will look something like this. I mean, if this 9 is here, okay, so let me just, so yeah, so the upper hull is going to be like this. All the points that are up to 10 to the left of this line are already processed, and all of the points to the left are either on the hull or they are below. So that's why it's called upper hull. Okay, so that's the invariant of the algorithm. We are going to incrementally build this, and when we come to Pn, it will correctly have the upper hull of all of the points. So that's incremental algorithms work like this. So they are correct up to a certain number of process points, and when that process point becomes the last point, it means that we have correctly constructed the upper hull for all of the points. Okay, so the idea is this: if you look at the upper hull, all the upper hull edges make a strict right turn at every step. For example, P1 to P3, P1, P3 to P3 to P6, it's a right turn. If you consider this line, it's a right turn. Then if you consider this P3, P6 line, it's a right turn. P6, P9 line, this to P10, it's a right turn. So we are always making right turns. Okay. Now, the algorithm is simply this. As long as you're making a right turn, you're fine. But when you come to a new point and it makes a left turn, for example, P1, P2, initially it was in the convex hull, upper hull. So the first time, then we process P3. As you can see, this is a very sharp left turn. If in order to have a right turn, P3 should be somewhere over here, okay? But it's not here, it's above there. So this left turn, we cannot have left turns. If you're going clockwise on the convex hull, you have to make always right turns. So this left turn clearly is a violation of convex rule. And which point is causing this violation? P2. Okay, because of P2 we are making this right turn, so delete that P2 from the upper hull. And we should do that as long as, for example, let's look at 11. Okay, so I'm just going to show you a case. When we come to P11, it's another right turn. So up to 11, all these 9, 10, 11, they're making right turns. But when we come to 12, okay, this is the left turn, a very sharp left turn from 11. So 11 shouldn't be on the list. But 10, what happens is that after we remove 11, we are moving from 10 to 12, which is also a left turn. 10 should also be removed. So we should have a while loop saying that as long as we are making a left turn, again from this 6, 9 to 12, it's another left turn, 9 should also be removed. So when we add point 12, in our while loop, we need to remove all these 3 points. As long as the last 3 points on the hull are making a left turn, remove the middle point. Or if the hull contains only 2 points, the middle point is not defined, so you will not remove anything. Okay, if your upper hull contains 3 or more points, and if the last 3 points are making a left turn, remove the middle one. That's the whole algorithm. We consider we go over all of the points one by one like this. When we come to Pn, we make sure that the upper hull, the list of points that remain on the hull, are all making right turns. And since we are all making these right turns, now we haven't talked about the correctness of the algorithm yet. I mean, with this rule, can we really make sure that all the points are below the hull? Okay, that this is, we have to prove correctness by making some arguments, by making some observations, and we are going to do that after we describe the algorithm. So I hope this is clear. And for the second lower hull, we do exactly the same thing. This time we start with Pn and Pn minus 1. N minus 1 actually is this. The cat is doing some mischief. So sorry about the cat. So he just dropped the bottle. Anyway, so this is Pn minus 1. So these are added to the lower hull first, and then we look at this, and again, as you can see, it's a left turn. So left turning once. Again, we are looking for, even we are going in backwards direction, we are not, still right turns are valid turns because we are doing things in clockwise order. Okay, when we are going clockwise, even in the lower hull, we should all be making right turns. Whenever we make a left turn like this case, it should be deleted. So we apply the same algorithm for the lower hull, and upper hull and lower hull are just then combined to get the whole convex hull. So the pseudocode of the algorithm is simply this. So yeah, it shows which points are deleted here. So here's the algorithm. The same input and output. We sort the points by x coordinate. Okay, now this is again An algorithm that we need to write here in step 1 is just indicated in one just sentence at a very higher level. So step 1 actually takes n log n time, and that's the dominating time complexity part. So step 1 takes the most time in this remaining steps of the algorithm. That takes n log n time. The remaining part of the code takes O(n) time. So this is for computation of the upper hull. Okay, put the points P1, P2, and starting from 3 to n, we append the new point to the upper hull. And if the upper hull contains more than 2 points and the last 3 points in L upper n do not make a right turn, so here strict right turn is taken into account, which automatically takes care of this degenerate case where 3 points are collinear. So if 3 points are collinear, okay, like in this case here, look at this edge, look at this edge, look at these 3 points. They do not make a right turn. If they don't make a right turn, remove the one in the middle. So the middle points that are not extreme points along this edge are removed automatically by this if condition, and because that doesn't, they do not make a right turn if they're on the same line. So the degenerate cases are handled automatically. We don't need to have complicated if conditions in this algorithm. And steps 7 to 11 computes the lower hull, and then step 12, since P1 and Pn they appear in both hulls, both upper and lower hulls, we remove them from the lower hull to avoid duplication, and we just simply append the lower hull sequence to the upper hull sequence to get the whole complete convex hull, and we return that from our algorithm, from our program. Okay, so it shows degenerate cases are handled automatically. And after the algorithm is described in the book, usually we will have a theorem, a mathematical theorem saying that the convex hull of a set of m points in the plane can be computed in O(n) log n time. So this theorem has 2 parts, and in many algorithms throughout the book, in different chapters, we'll have 2 parts that are stated here. First of all, it tells that the convex hull can be computed, meaning that there is the correctness proof. The algorithm is correct, and it runs in O(n) log n time. So we try to prove both the time complexity and the correctness. And if you look at the proof, the first paragraph is about correctness. The second paragraph is about complexity. All right. So as you can see, it doesn't look like a formal proof at all. It's just some English sentences written in free text, but still a proof because it uses proof by induction to prove the correctness claim, and it makes correct claims, and it makes statements that are mathematically or geometrically also correct. So it convinces you that the upper hull is computed correctly. And in terms of computational complexity, again, we just make English statement arguments saying that, okay, it looks like if you look at the algorithm pseudocode at first, doesn't look like I mean, this from steps 8 to 11 doesn't look like it's O(n), right? It looks like it's, I mean, if you showed this to a newbie, a new programmer, they will immediately say it's like n square, because there's a for loop which goes n steps, and there's a while loop which potentially also goes n steps, because we may be deleting many points. So the while loop may run n steps too, n steps, n steps. So it should be n square. So nested loops, right? But the answer is wrong. Oh yeah, actually the algorithm also addresses the robustness problem automatically. I'm going to discuss that. But if you look at this computational complexity, it's not n square actually, because when a point is deleted, it's deleted forever. I mean, the total number of while loops, the while loop is going to be executed at least once per iteration. But all the additional times the while loop runs, it's to delete a point. And the total number of while loops in all of the for loops, their summation, the total number of times the while loop runs cannot be n squared, because we have at most n points. You may delete at most n of them. So therefore, the while loop, this total running time of this while loop is not n squared, it's actually n, because when a point is deleted, it's not processed again, it's deleted forever. So hence, this takes O(n) time, and this takes n log n time, and this has the computational complexity, time complexity is n log n. Now, let's discuss the robustness. What happens, for example, when we have this floating point errors? For example, a point is very close. For example, look at this point here. What happens when we come to here and we say it doesn't make a right turn? So what we may do is, since this upper hull, it's always going to be a chain of edges. We will not have an empty chain. I mean, this point itself may left, because of floating point errors, it may be left outside the hull, but it will still be, if it's so close to the hull edge itself, it causes because of floating point error, we treat it as if it's inside. It means that it's very close to the convex hull edge, and the convex hull we get is going to be very close. It's a very close approximation to the real convex hull. So we will never have, because of this algorithm is designed, we will never have empty edges or multiple edges. So it will always be from x to right, from smallest x to largest x. It will be a chain of edges. Another thing about degenerate cases is what happens when we have this 2 points with the same x coordinate. If you sort them by y coordinate, again, it's automatically solved. So we can discuss the robustness. I mean, the book does not discuss the robustness in very detail, but the proposed algorithm is more robust than the previous one. We can talk about, there's no such thing as fully robust. There can always be cases that you haven't thought about, but we can at least compare two algorithms and compare them with respect to their robustness. And I can see that the second algorithm, in addition to being more efficient, it's also more robust, because it will never result in an polygon that is incomplete or not simple. It will always result in a polygon which is convex and simple. The final thing I want to discuss is the correctness. The correctness proof works like this. It's by proof by induction. By definition, the first 2 points, P1 and P2, for example, P1 and P2, up to this point, there are no other points, so all the other points lie below it. So what we want to prove is this. When we come to Pi, when we process Pi, when we construct this hull, all the other points should lie below the hull. It should be a valid upper hull. So given that all the points up to P1 minus 1 is a valid hull, addition of Pi, is it still going to be a valid hull? Okay, so we try to discuss this. And the algorithm just, the way the points that can invalidate addition of this Pi. We know that Pi should be strictly to the right of Pi minus 1, right? Because we are processing the points with respect to sorted x coordinates. So it has to be to the right. It may be up here, it may be lower here, okay, doesn't matter. But what matters is that a point that is going to invalidate the addition of Pi to the upper hull is a point that should appear on the top of upper hull. For example, can there be a point here? There cannot be a point. This empty region should be empty because of the induction hypothesis that the points up to Pi minus 1, they form, the points here or the vertices form a valid hull. Therefore, we are sure that the induction hypothesis shows that, assumes that this is really an empty region. So addition of Pi, what we want to prove is that this whole region is also empty. Okay, and we can actually see it right from the figure. Okay, this part of the figure was already empty. Okay, so since it's I mean, can you add a pi here in which this region will not be, I mean, the part that is to the left of pi minus 1 is which is white shown here, is actually the new empty region. We cannot have that. I mean, if you just put any point, it may be below here, above here. If you put any point towards the right of pi minus 1, this empty region will not be affected by that. All right, it will still remain empty. The only thing that can invalidate the correctness of the upper hull is a point that appears above the hull in the vertical slab between pi minus 1 and pi. So can there exist a point that is above the hull in this region between pi minus 1 and pi? And that's impossible, because if there's such a point, it means that it would have to be in x coordinate between pi minus 1 and pi, and there's no such point because we have sorted them with respect to their x coordinate. There can be basically no points between pi minus 1 and pi. If they have equal x coordinates, we can ignore those equal x coordinate cases, but even in that case, they will not invalidate the case. I mean, if this pi, for example, if there's a point here above pi on the same vertical line, just under this mouse cursor, in that case, that will be pi plus 1, which we will consider next, okay? Because we have sorted with respect to y coordinates if they have equal y coordinates. So that will be pi plus 1. There can not be another point before it that will invalidate this. And this pi plus 1 actually will delete this from the convex hull pi, so that it will still be a valid hull. Okay, so this case is made in English, saying that there can be no points between so like proof by not contradiction, but we are using proof by induction and claiming that there can be no points in between these two, because that's the way we constructed our point set. We sorted them with respect to their x coordinate, and this sorting is really important. We cannot just process the points in arbitrary order. If you process the points in arbitrary order, you may get an incorrect result. Okay, so this was just a sample of what we will be discussing in the book in different problems. I will show you an algorithm. We will discuss its correctness. We will discuss its computational complexity, sometimes space complexity, and we will make some geometric observations, and we will have different algorithmic techniques. So this time we had an incremental algorithm. In different cases, we will have randomized algorithms, plane sweep algorithms, or maybe divide and conquer. So we will see different algorithmic techniques and data structures to solve the problem more efficiently. Okay, so in this now last part of the lecture, I want to talk about the new computational geometry. This will be your first computational geometry specific algorithmic technique, which is the plane sweep technique. So it's actually discussed in chapter 2. Let me just go below chapter 2. Yeah, line segment intersection. Okay, but before I discuss line segment intersection, I want to just talk about this problem that to introduce plane sweep algorithm, I'm going to talk about this closest pair problem. In closest pair problem, just like convex hull, we are given a set of points on the 2D plane. Okay, lots of points, and two of them may be closer to each other than the rest of them. Okay, our goal is to find this. And there's a question I missed. In terms of robustness, in terms of floating point in the previous problem of convex hull, in terms of floating point errors, we are still sensitive to those floating point errors. We cannot avoid them. there are actually libraries which try to do exact arithmetic, but they are very slow. There are some certain techniques that use symbolic representation of those so that we have exact arithmetic. But most of the cases we do not. I mean, if you're doing with floating point operations, we actually accept these small errors. For example, usually when you're testing equality of points, you just use an epsilon, like 10 to the minus 6, for example. If 2 points are closer to each other with 10 to the minus 6, then you consider them as the same points. If your convex hull is that edge is close to a point with 0.06, I mean, not, sorry, 10 to the minus 6, you may consider it to be on the edge. So yeah, we are still sensitive to those floating point errors, but it will at least lead valid results. That's what robustness is, not to crash, not to produce something that is not a valid polygon, for example, if you're looking for polygons. All right, so we will be sensitive to floating point errors, but we will be able to produce output even in that case. Now, so let's get back to this closest pair problem. The geometric observation we are going to make is actually not that. I mean, there's no geometric observation here. So we are given a bunch of points. Imagine you have 1 million such points, 10 million such points, and your goal is to find the closest pair. Now, without using any algorithmic technique, an obvious solution is an ON square solution in which you check the distance between every pair of points and you keep track of the minimum distance. This will be ON square. But in order to be able to reduce this n square to a smaller complexity, we should try to find techniques to avoid computation of distance between all of the pairs of points. So for example, if you know that these 2 points are of d distance away, for example, if the distance between these 2 points, let me get back to the red one. If the distance between these 2 points are d distance, for example, I should not check. Consider this point, for example. Consider its d distance to the left, d distance to the right. Okay, should I check the distance of this point with this one? No, right? I mean, because it's impossible for this point to have a closer distance than d. So if you already know you have found something, the current minimum distance is d, you don't need to make distance computations to points that are outside this range. So we will actually be making use of this observation to speed things up. So in order to do that, we need to introduce something. We need to process these points in certain order. We are going to sweep the plane either from left to right. Okay, we call the line. This is called the plane sweep algorithm, and this is called an important element of this plane sweep algorithm is the sweep line, in which we use it to sweep the plane in certain direction. This can be from left to right, or right to left, or top to bottom. In the book actually, the sweep line will be from top to bottom. Okay, in the line segment intersection problem, the examples that are given are a sweep line that is from top to bottom, or it may be bottom to top, it doesn't matter. Or it may even be in some arbitrary orientation. You may have a sweep line in an arbitrary orientation, but it will make implementation very difficult. Okay, you don't want to do that. Okay, so sweep line is an important element of the plane sweep algorithm. So we are going to sweep the plane from left to right. Actually, in convex algorithm that in the book, we were also sweeping the plane, right? I mean, we sorted the points in terms of their x coordinate, and we were sweeping the plane from left to right. So it's also the algorithm that is given in the book in chapter 1 can also be considered a plane sweep algorithm. Now, another important element of a plane sweep algorithm are event points. Okay, because when we are event points, so when we are sweeping the plane, we are not sweeping in a continuous manner. We don't need to sweep in a continuous manner because from here to here, for example, when the sweep line moves from here to here, nothing changes. This current state, I didn't start with any point. There is no point I have encountered yet. And during this sweep, you don't need to continuously sweep from here to here because nothing changes. So we actually have, in a plane sweep algorithm, we have discrete event points in which certain things change. We get ourselves new information. We encounter a new point. For example, therefore our sweep line is going to jump from event point to event point as it goes from left to right. And these event points sometimes will be static. In the case of this closest pair problem, the event points are just the points themselves, the input points that are sorted with respect to their x-coordinates. So you can just have a sorted list of your points with respect to x-coordinate. That may be your event point list. But in general, sometimes we may discover new events as we go along the sweep. As we are sweeping the plane, new events may be discovered that you may not be aware of before at the beginning of the problem. Hence, we use a data structure named a queue. Okay, just like we use like a priority queue, which we call an event queue. Okay, so the event queue is it's a list of these discrete events that are put in a queue, and it allows operations like give me the next event. So it's like a priority queue, prioritized based on their x coordinates. So therefore, when I'm moving the sweep line, I should be able to say what is the next event? What is the next event? Give me the next event. So we can, in O1 time, for example, in an event queue, we can get the next event easily in O1 time. But it should also allow for addition or deletion of certain events. Sometimes you may discover that certain events are no longer relevant and we may want to delete them from the queue. Sometimes when we discover a new event, we may want to insert them into the queue. And these insert and delete operations should not take more than log n time if you want to have an efficient algorithm. Okay, because we will have n steps like this. We don't want to have more than, it should be, this event queue, if you just implement a regular priority queue using heaps, for example, you will be able to insert from the heap in log n time, insert to the heap, delete from the heap in log n time each, and you can get the top element, the minimum prior or maximum priority element from the queue in O1 time. So event queue may be dynamic. We will see that's dynamic in the case of line segment intersection. But for our case, the event queue is just a static list of points from left to right. That's another important parameter, the element of a plane sweep algorithm. The next important element of the plane sweep algorithm is called the status structure. Status structure, let me write in the chat box, status structure. It actually shows the current information about the sweep line, and it stores elements in it which is necessary to handle the next event. Okay, that status structure, for example, what I will be doing is that, imagine it will be something like this. After I process the second event, I will maintain the D. The D will be a variable which maintains the current minimum distance between 2 points, and it will be updated accordingly if I find a smaller distance D. And what my status structure simply be is going to be a set of points that are in this vertical slab of width D. All right, just consider this set. Okay, now actually instead of using the set, I will be using the same thing in the book, tau. This tau is used to indicate, it's the variable the book uses most of the time to indicate the status structure. So this data structure tau for our case, for example, maybe a set of points that are in this vertical slab D. The study structure should also allow deletion and insertion of new points efficiently. We should be able to insert into the study structure in log n time and delete from the study structure in log n time. But unlike priority queue, sometimes it may also allow for range queries or neighborhood queries. Therefore, usually for study structure, we will be using a balanced binary search tree, AVL tree, red black tree, whatever it is. Or if you're implementing this in C++, you can use the set data structure in STL, which is actually implemented like a balanced binary tree, which allows range queries, insertions, and deletions in log n time. So now, after I describe these elements of a plain sweep algorithm, I think the algorithm is now clear to you. I mean, with these elements, you should be able to solve this closest pair problem efficiently, right? So at every new event point, we will handle that event like this. When we come to a new point, we tested the distance of this point with all the points in our set tau, okay, in our study structure. If there is a smaller distance, we decrease. I mean, this way we avoid test of this new event point that are to the left of this vertical slab. All right, we just test it against this because these are potentially the points that may have shorter distance than D, all right, when we come to a new event point. So every time we are moving to the next event point, elements that remain to the left of this vertical slab are deleted from the study structure, and only the points inside the study structure are tested against this to check the distance. Okay, now here's the problem. Does this guarantee n log n running time as we move from left to right? Okay, adding new points to this, deleting some points, there are n events in total. So since there are n events in my event queue, my main loop is going to run n steps. So at every step of my handling of a point, I should not spend more than log n time, right? If you want to have a n log n algorithm, there are n steps. So when you're processing a point, you should not use more than log n time. Now that's a problem, right? What if there are lots of points in this slab? For example, it may be the case that all of your points are in a very narrow, thin vertical slab. If the study structure is a set like this, okay, it will allow deletion and insertion log n time. But if we test our point against all of the points inside this, we cannot guarantee log n running time. Any ideas to how we can speed this up? So here is how we'll do that. Do you really need to look at all the points here? Yeah, the principal component, the set actually, we can have this set. This, as I said, binary search tree, right? Balanced binary search tree. How are we going to insert these points? They have their XY coordinates, right? How do we add a point with XY coordinate to this balanced binary search tree, which just use a single item as value as key most of the time? Do we add these points to this tree with their X coordinates? What if I add these points to this balanced binary search tree with respect to their Y coordinates, which will allow me to make a query, a range query with respect to Y coordinates? So look at this. This is the new point here, okay? This is the new point. Do I really need to test this new point against all of the points? No, right? I mean, if there's a point, look at this distance D. If the distance in the Y direction is also larger than D, a point outside this region cannot be a candidate of a shorter distance. So what we do is, from the study structure, we make a range query. If this point is P, okay, we make a range query with this range, Py minus D, and py plus d. Okay, look at these values. It gives you a range in the study structure, and it will you can do this range in log n time if you have the balanced binary search tree in which the points are inserted to this tree in terms of their y coordinates, and then you can make this search in log n time. It will return you all the points that are in this rectangular box, which is of height 2d and width d, and then you may test all the points that are here against your point P to compute the distance. Now, another question. What if we have, okay, this was a rectangle of size d and 2d, right? What if we have a lot of points inside this rectangle? N of them. Can I still do this in log n time? I mean, I did the query in log n time, but there are many points inside. I still need to check my point P against this many points. In that case, if I do it in log n time, I do it n times, I will have an n square log n algorithm. Still, I cannot do n square. Okay, so, but the question is this possible? Can you have many points inside this 2D rectangle? I mean, inside this rectangle? The answer should be no. Because at this point, when I come to this point P, I know that. What is D? D has a very important meaning. It's the closest distance between the all the points that I have seen to the left of this sweep line. So this was the sweep line, and D is the distance between the smallest distance between the pair of points to the left of this line. Now the question is, if I give you a rectangle like this, D2D, how many points you can put inside this rectangle such that their distance is not smaller than D? You cannot put this many points. As you can see, the distance between them is smaller than D. I mean, the largest number of points I can put on this rectangle is 6. I cannot put more than 6 points. Okay, and at the boundaries. If I put any point anywhere, the distance is going to be less than D. All right, so you see this, right? I mean, if the minimum distance between the points up to now is D, and if you look at this rectangle cannot contain many points. The final thing in terms of time complexity proof that we are going to make, the claim we are going to claim, is that this rectangle contains all 1 points, which means a constant number of points, 2, 3 maybe, but still constant. It cannot be more than 6. It's a constant number of points. If there are a constant number of points, if you multiply that with log n, you did log n, and for a range query, you are testing it against this many points, which means that you will not be spending more than log n time. So actual log n plus O1 to check the distance against all the others. So this is what this is the time you will be spending at every handling of an event point. And since there are n event points, the final algorithm is n log n time. Okay, so the algorithm is simple to describe, may not be so simple to implement, but it has the main structures of this algorithm. We have a queue, event queue of points. We have a study structure which is extremely crucial to have an efficient algorithm. For example, we figured out that the study structure should be a set. It should be a set of points that are inside the vertical slab with D. And as we move this line towards right, I need to delete points that are no longer inside this vertical slab. I'm inserting, when I'm handling an event point, I'm adding this new point to the study structure. It's now in the study structure. And also, I'm making queries in the study structure with respect to y coordinates. So these are really important components of this study structure, and most of the time a balanced binary tree, search tree, which has to be balanced to guarantee log n query time and insertion deletion time also is needed. All right, so these are the important components of of any plain sweep algorithm. The line segment intersection problem is a lot more difficult than this simple closest pair problem. Closest pair, the simplicities are, for example, the event queue is static. No need to add new events as we move. This is an important observation. Actually, one of the heart of the algorithm is to figure out that we can actually limit the number of distance computations to points within this window. That's the part that guarantees n log n running time. If you just maintain the entire thing as a set and try to test everything, there can be worst cases like this, all the points that are in a thin vertical slab that will have larger running times. Okay, so this is the closest pair solution by plain sweep. You can actually think about other solutions to this closest pair problem, like maybe divide and conquer. If you divide the point set into two parts, find the closest pair here, find the closest pair here, will it help to find the closest pair? It may. I don't know. I mean, there may be different algorithmic techniques that you may use to attack this problem. And plain sweep is just one of them. But plain sweep is a very widely used technique in attacking geometrical problems. Plain sweep is used in Voronoi diagram. Fortune's algorithm for the Voronoi diagram actually is also a plain sweep algorithm. The line segment intersection problem we are going to see next is also a plain sweep algorithm. So with that, I'm going to turn our attention to the line segment intersection problem and we'll see the commonalities with this plain sweep algorithm and differences, like the event queue will be static, and we will have to do observations like the log n query we did here, this range query. We will do it in another way for line segment intersections. Okay, so let's now move into the new problem. Do you have any questions about closest pair or plain sweep in general? All right. I mean, if you have questions, you can always write in the chat box anytime. All right, so the line segment intersection. This chapter actually has two parts. The first part is the line segment intersection. The second part is map overlay. If we are given two maps, which are like two subdivisions of the same plane in different ways, so lots of polygons. Like, imagine a map, a city map. Okay, then there may be a vegetation map which shows where the forests are, where the fields are, things like that. So if you want to overlay these two maps, how can we do that? That's the actual problem the chapter tries to solve, but it uses line segment intersection as the first step to approach this problem. So the first part of the chapter deals with that. We will continue with this chapter to next week, focusing on the overlay problem. But this week I'm going to describe you this line segment intersection problem quickly. I will not have a break, and I will try to finish in 15 to 20 minutes. Okay, we will finish today's lecture around 12. I will just spend 20 more minutes to describe you the main algorithm of line segment intersection, because we have the main components of our plain sweep algorithm. So the problem is this: we are given a set of line segments, and our goal is to report the ones that are intersecting. There are six line segments here, and there are about a number of intersections that are almost linear in the number of them. If the number of intersections is large, we cannot avoid quadratic running time, but our goal is to avoid intersections tests between all the pairs of lines. Again, the naive solution will be just like the closest pair problem, to test the intersection between all the pairs of line segments, which will clearly be n square running time, but we want to reduce that. Okay, so here is one observation we can make. If the y-axis projections of these line segments do not intersect, if the y-axis of the, look at the y-axis projections. If I have two lines here and their y-axis projections do not overlap, it's impossible that these line segments intersect. All right. Now, and this is not an if and only if case. I mean, if their y-axis projections overlap, it may be possible that they do not intersect. It's not, but it's a necessary, overlapping is a necessary condition. But if that condition is satisfied, it's not the sufficient condition to intersect. It's a necessary but not sufficient condition, y-axis overlap. So this observation can be turned into an algorithm, plane sweep algorithm like this. Let me, by the way, there's a noise coming in from one of your microphones. Maybe it's me, I'm not sure. But if you can check your microphone and mute it, somehow my mute all button do not work. Okay, so there's this rhythmic noise I hear in the background. If you can check your microphone and mute it, it will be appreciated. All right, so let's talk about these lines. Okay, we have these line segments. Some of them intersect, some of them do not intersect. So here is the algorithm, the plane sweep algorithm. Since we are looking at y-axis projections, our sweep line will be a horizontal line like this, which we will move from top to bottom. So, and our event points obviously are the endpoints of the line segments, and we will distinguish between beginning point of a line segment and end point of a line segment, because this is what we're going to do. The study structure will simply store the current set of line segments. So for example, when I come here and the sweep line is here, the study structure tau is going to store the line segments that are currently intersecting with this line. All right, so it will now contain 1, 2, and 3. Okay, so when I come to 4, for example, when I come to the endpoint, an event point, which is an endpoint of a line segment, the sweep line is going to cease to intersect this line segments. Hence, it's going to be deleted from the study structure. When I come to a beginning point of a line segment, it's going to be inserted into the study structure. So the study structure is a set of line segments currently intersecting with the sweep line. So all I need to do is, for example, if I implement the algorithm like that, when I come to an event point in which the line segment is the beginning endpoint, the line segment starts intersecting with the line. It also means that its y-axis projection overlaps with all of the other line segments that are currently on the study structure. Okay, you see you understand what I just said? If a line segment starts intersecting the sweep line, if it's inserted to the study structure, at that point, whatever other line segments are in the study structure, the y-axis projections overlap. So we should test it against all the lines that are currently in the set. Okay, now and so I'm inserting and deleting from the study structure like this. Okay, so, and what I also do is, okay, the study structure, again, if I treat it as a set like this, there may be cases in which all of the lines, for example, let me get a new figure. Consider the x-axis. What if I have line segments and all of them intersect the x-axis? What does it mean? It means that at some point in my study structure, I will have all of the lines in the study structure. So it cannot give me any efficiency at all. All right. But just like we did in the closest pair problem, what if I store these line segments into the study structure tau in some order? What kind of an order can they be? I mean, I have a line segment, this time not just x and y coordinates, but 2 points. Okay, if you're going to store them into the study structure with respect to their y coordinates, x, y, which y coordinate is going to be? I mean, is it going to be this one, this one? Yeah, just think about how you're going to insert these line segments into the study structure in some kind of an order. And the order that we will be using is this. Given a study structure, although they have two different y coordinates, beginning and end coordinates, at any point of the sweep line, at any point, if you just consider the order of the line segments that intersect the sweep line at these intersection points and use these intersection points as a way to order those line segments and store them in the study structure like that, that will be some kind of an ordering. All right. Now, if I do that, look at these two line segments. For example, 3. At this point, 3 is before 1 in the study structure. But when I come here, 1 is before 3. So their order changes. Where did their order change? At this intersection point. Okay, so immediately this tells me that if there are intersection points that I discover, they should be event points in which certain things change. For example, the study structure changes. All right, so that's really important. So what we need to, here that's why the event queue in the line segment intersection problem is not static. As we discover intersections, we add intersection points as events to the event queue, and at those events we need to make changes to our study structure so that the order of line segments on the study structure change. Okay, that's one thing that we need to do. Now, how can we make, let's now think about this case. How can we make intersection tests? For example, when a new line segment comes here, how can I avoid testing this line segment against all of them that are currently in the study structure? Am I going to do again a query with respect to some D, range query? What is that D? What will be that D? Any ideas here? You can write in the chat box. So when a new line segment enters the study structure, I have lots of line segments in the study structure, and I want to avoid testing of the study structure against all of them. Which ones am I going to test intersection with? What kind of a range query am I going to perform on the study structure? Any ideas? Okay, let me tell you the solution. I will just test this against its neighbors. Wherever point it's inserted in the tree, I will test it only against the immediate neighbors. So this brings us, this requires a very important geometric observation to make, actually, which is like a lemma in the book. In order for two line segments to intersect, they need to become neighbors at some point in the study structure. So here, it's here in this lemma, right? Yeah, here. Lemma 2.1, which indicates our this becomes basically our important geometric observation. Let SI and SJ be two non-horizontal segments whose interiors intersect in a single point P. So if there's an intersection between SI and SJ like this, SI and SJ has to become neighbors in the study structure at some point. With that, we can actually have the overall algorithm designed easily. We will just be testing neighbors. And the degenerate cases in which multiple lines intersecting at the same point, multiple line segments intersected at the same point will be handled easily by making small modifications to the algorithm. But this is basically what we will be doing. We will test whenever a new line segment comes into the study structure, we will test it with just its neighbors. And deletion of certain, for example, it may be the case, let me draw it here. Okay, imagine there's a line segment here. This one entered, okay, and this one entered here, and their intersection is way below here. Okay, now so this is the sweep line. When the sweep line comes here, this let's call this line segment 1, let's call this line segment 2, let's call it 3. So when segment 2 is inserted into the study structure, it's not neighbors with 3, right? It's neighbors with 1 and whatever line segment that is to the left. Okay, so if we have this case, 2 is tested against 1, no intersection. 2 is tested against this, no intersection. Then we come to the sweep line comes to this point. 3 is inserted. Again, it's not neighbors with 2. It's not against, again, it's not tested against 2. At the time of insertion of the line segment, we don't make the correct intersection test between 2 and 3. But when do they become neighbors? They become neighbors when we come to this event point. When we come to this event point, what happens? The segment 1 is deleted from this study structure. So when we delete something from the study structure, 2 line segments that were not neighbors before may become neighbors now. So deletion events will cause some intersection test to be made. When we delete something, whatever was to the left of this deleted segment and to the right of this segment, when it disappears in between them, these 2 become neighbors and tested for intersection, and this intersection point is found at this event point. Okay, the intersection point between 2 and 3 is found at an event point that is attached to 1. Okay, so this is really something we should care about, but the algorithm is really very similar to plain sweep in this regard. What we have here is that a sweep line in which we are going to have in our study structure the line segments that are currently intersecting the sweep line, and we will this will be a balanced tree. Let me show you the figure from the book, which will make it much clearer. So it will be something like this. Look at the study structure. This is the sweep line. These are my line segments here. As you can see, at this status of the sweep line, they appear as Si, Sj, Sk, Sl, M like this, and they appear in this balanced binary tree with respect to the points they intersect the sweep line at this point. And let me ask you, for example, as I move this line continuously down, the intersection points change. Okay, look at the x coordinates of these intersection points. Oh, the event point in this algorithm are the endpoints of the segments, line segments, also the intersection points as we discover them. So the event points are not determined beforehand. The endpoints of the line segments are the event points that are initially inserted into the event queue, but as we discover intersections, we need to insert those intersection points as event points. Because what happens in the event point, as you can see, as we move the line down continuously, the order of the lines on the study structure do not change at all. I mean, their x coordinates change, the intersection points with the sweep line changes continuously, but do I need to change my study structure because those intersection points move a little bit towards right, this one moves a little bit towards left, this one moves a little bit towards right? As they change dynamically as I move the sweep line continuously down, they do not require me to change the study structure because their order is still the same on the line. When do their order change? At an intersection point. Look at Sk and Sl. At an intersection point, their order changed. Since their order changed, the neighborhoods also changed. Now Sl became neighbor with Sj. Sk became a neighbor with Sm. So neighborhoods and orders change. So therefore, intersection points are event points. Okay? So I'm going to talk about the details of the algorithm continuing next week, but I just want to show you the pseudocode of the algorithm and how it works and how it looks like initially. So if you look at the main algorithm, find intersections, It's really simple, just 5 lines of pseudocode, and actually it doesn't do any. I mean, it's just the outline template of a regular plain sweep algorithm. As you can see, there's an empty event queue. Some event points that we initially know are inserted into the queue. So we initialize the event queue, with the endpoints of the line segments. And we have a status structure. We again initialize it as an empty status structure. And while queue is not empty, as long as we have new events to consider, get the next event with the highest priority from the event queue, delete that event, and handle that event. Okay, so the entire actually thing is, how do we handle this event point P, and what is stored with this P? And here is a case figure that shows all the degenerate cases where this event point P is really something. There are line segments that end at this event point, like S4 and S5. Look at S4 and S5. They should be deleted from the status structure after this event is handled. There are line segments like S2, which enters the status structure at this event point. S2 is going to be inserted. So this is the snapshot of the status structure before handling of event point P. This is the status structure after handling of event point P. And there are also line segments in which this event point P is there in their interior. Okay, they will remain in the status structure. But what happens is that if you look at S1 and S3, S1 appears before S3 in the status structure, but after the event point is handled, S3 appears before S1. As if you look at this event point, all of these segments other than S7 and S8, okay, S7 is going to be the leftmost leaf node, S8 is going to be the rightmost leaf node, but all the ones in the middle, they have their intersection point with the sweep line is the same, right? Their x coordinate exactly is the same. So how do we order them? For example, how did we came up with this order of S3, S2, and S1? What we do is that when we are handling an event point, we actually order these lines in an imaginary sweep line that is epsilon below this actual sweep line. So when we are going to find their intersection points with the sweep line, we assume what will happen if I move the sweep line slightly down so that they are no longer at the same intersection point. If we do that, we can clearly see that S3, S2, and S1 appear in this order. If you move the sweep line epsilon down, and therefore when we are inserting into the status structure our comparison function with respect to x coordinate, because you need to have, if you want to add something to a balanced binary tree, you need to have a comparator. Either you're using less than operator or something. I mean, balanced binary search tree should have a way to compare two items inserted to it with respect to some key. Here, the key is the x coordinate that they intersect the sweep line, but that x coordinate is found by just not the exact location of L dot y, its y coordinate, but L dot y minus epsilon. Okay, so you need to consider this to find their keys at the time that they're inserted. All right, and as you can see, the handle event point function is like 16 lines long. It defines 3 different sets. The set of line segments that will be deleted, in which their lower endpoint is this event point. The set of line segments in which this event point is their upper endpoint, and the line segments in which the event point P is in their interior. So it defines these 3 sets. And if the union of these 3 sets contain more than one segment, then it must be an intersection. Okay, and what it does is it deletes segment 4, 5, 1, and 3 from the status structure. 1, 3 is also deleted. Okay, and then they're reinserted. So we the reordering of 1 and 3 is going to be established by first removing them from the study structure, then reinserting them at this sweep line. Okay, they will order them correctly. And then find new event is the way we test for intersection between the neighboring points. So these three find new event function calls actually are the ones that we do the intersection test with the new neighborhoods that occur. The new neighborhoods that occur are, for example, S3 became neighbor with S7, S1 became a neighbor with S8, and the things here, they're also neighbors. The thing that is inserted newly became neighbors with its left and right neighbors. So all these intersections are tested, but if you look at them, there are constant number of such intersection tests. There is no for loop here. Okay, there are unique one number of segments that are defined. We call this function only a constant number of times. And if you look at the find new event function, it's this. If there's an intersection below the sweep line, add it to the event queue. Otherwise, don't do anything. This is find new event is that simple. Okay, we will discuss the details of this algorithm next week. But I just described the overall architecture of this plain sweep algorithm to solve the line segment intersection problem. There are really tedious things in terms of implementation. For example, how you implement this epsilon thing, ordering of line segments. It will be very difficult to implement this algorithm. But if you understand it at a higher level, it will be sufficient for this course. All right. That's it from me for today. We will continue with the details of this handle event point function. We will finish line segment intersection, and we will start the map overlay problem next week and finish chapter 2. So the goal for next week will be to finish chapter 2. All right. So that's it for today. If you don't have any questions, I will end the meeting. Okay, I think there are no questions. Thank you for attending. As usual, I'm going to post the links to the recorded videos on OttiClass. See you all next week. Thank you. Bye-bye. Have a nice day, you too. Let me stop recording first.